So following on from the previous video, we were trying to develop the fundamental theorem of calculus 2. So normally we would have a function f of x, but because x is reserved for something else, we have to change the name. Otherwise the two would clash. So we're gonna represent we're gonna use x to represent this vertical height here. So x can slide back and forth, but we've got to change the name here. We've got to change the name, otherwise the two would clash. So when it comes to the fundamental theorem of calculus 2, we are concerned about this area here. Okay, so we are just going to call this area, let's give it a name, capital F of x. So this thing here represents the area here. Well, this area here can be written as this. Can be written as the integral from a to x, and then the function f of t, and then dt. So this is for this. Hang on, t being somewhere in between a and x. So this bit here. Well, don't forget, this here is just us naming the area. Nothing special about it. It's just us assigning a name to the area. This here is a way we would write the area. Okay, so this here represents the area. It's just a name we assigned to the area. This here is a way we would write it. So now if you look at this, so what we've done here is that what we've done here is that we've in a way created we've created a function. So no matter where x is along here, x can slide back and forth here. So let's just say it's currently at a location, whatever location here. When you put x into here, this function here will spit out a value to represent the whole area. So this will spit out an area. So suppose x is here. So if you put this value here into this function here, it will spit out a new area, but then it will spit out one number. Well, that one number, this one number here, represents the area. So suppose x is somewhere over here. If you put this location into this machine here, it will spit out a number. Well, this number here would represent the area from a to x. So the point here is that this here is really you can think of it as a function, because no matter where x is. Hang on. So let's start again here. So we, with the fundamental theorem of calculus 2, we're concerned about the area from a to x. Okay. So this here is just us assigning the name, and the way we would write it is from a to x, and then the function itself, dt here. So what we've done here is that we've in a way created a machine here where no matter where x is, if you put it into this machine here, it will spit out a number. Well, this number here will represent the area from a to x. But here's the thing. Hang on. So this is like a function here. You put the location in this thing here, and then it will spit out a number that represents the area. Well, if that's the case, then you can draw a graph of this thing here. You can draw a graph. So it looks, I don't know, I'm just making it up. It looks something like this. It will be a function. So this is your capital F here. So what we've done here is that this here is an area. Capital F is an area, but then we really translate it into a line graph. So in a way, because we've in a way translated an area into, well, this is a function. It spits out one value, so therefore we can turn it into a line graph. But here's the thing. Looking at this line graph, and this line graph is in a way the area here as x slides back and forth. Okay, so looking at this line graph, you can now differentiate this line graph. You can actually differentiate this line graph. And here's a weird thing. When you differentiate this line graph, when you differentiate this line graph here, Don't forget, this also represents the area here. When you differentiate this line graph, it actually turns out to be this thing here. Just we're going to prove and see why this is the case. But in short, we used x to represent this vertical line here. With the fundamental theorem of calculus 2, we are concerned about the area from A to x. So we would use this to represent. We would use this to label this area here. But then we translated this area into a line graph. We translated it into a line graph. And then the thing is, when you differentiate this line, it actually gives you, hang on, this thing here was this, well, x f of t dt. When you differentiate this line graph here, it will give you back this thing here. We will try and understand why in the next video. Okay, but the important thing here is that we've visualized the area. We've translated the area into a line, and then we would then differentiate this line, and then for some strange reason it would give us this. The concept is quite clever. We've translated an area into a line, and then we would then differentiate this line. I will elaborate more on it in the next video.